Hi viewers, good morning all of you. Assalamu alaikum. This is the month of Ramzan, Holy Ramzan, and mashallah, this is another video which I am bringing to you regarding response spectrum analysis. Let us discuss its concept. Consider a building, a small structure, or any object. When you push it and when you leave that object, it will vibrate, right? It will vibrate, it will have its own vibration. So when it is vibrating freely, okay, when it is vibrating freely, the time period at that time, it is called natural time period. Okay, and also the time needed by a structure to complete a free vibration cycle is called natural time period. Mainly it depends on the mass and the stiffness, both mass and stiffness of that structure. Heavy buildings vibrate slower than lighter buildings. For example, when you have when you consider a car, okay, and any lighter material, you take any electric pole. When wind blows, okay, so both of them will vibrate. Both of them will vibrate. But as this car is a heavyweight and this is a electrical pole is lighter, so electrical pole when comparison, yani when compared the car with electrical pole, you have in car, yani this will be having more vibrations than the car. Okay. Similarly, when stiffness increases, time period decreases. When stiffness increases, time period also decreases. For example, another example I want to give you. Let us consider a building. It's a framed building. Okay. And also we will have at the same time we have a building without frames, and it's having shear walls type. All around you have the shear walls, you don't have any frames inside, it's just a frame. So definitely stiffness of this building is more than stiffness of this building. Okay. So when stiffness increases, time period decreases. So the time period for this will be definitely lesser than this. Lesser than this. Yani if you consider T1 and T2, so T1 will be lesser than T2. And here similarly, if you consider this as frequency N1 and N2, you will have N1 is lesser than N2. Well, now short buildings are stiffer than tall buildings. Short buildings vibrate faster than tall buildings. because here stiffness is more when compared with the tall buildings. So short buildings vibrate faster than the tall buildings. It means that time period of shorter buildings is lesser than the time period of the longer buildings. So now we got one question. We will get one question that why are structures affected by earthquakes? It's a big question. Why are structures affected by earthquakes? Let us see now. If light buildings are hit by earthquakes, they will not affected much. When we add mass at the top, there is a difference in the motion at the base and at the top. Relative displacement causes forces generated in the building. So when we have the mass at the top and we have a motion at the base, okay, like this is one frame, this is the mass, okay, sorry. So when we exert force, when we exert force at the base also, and there is a displacement here, okay, so this response due to the force, okay, at the base, that is nothing but the earthquake, okay, is measured by the relative displacement. This is called the relative displacement, okay. So now relative displacement is nothing but V is equal to U into K. Oh sorry, it's not a relative displacement, it is the shear force. Shear force is nothing but the relative displacement times stiffness. And similarly, acceleration is nothing but U into K by M, where V by M is equal to acceleration. How we got this formula? We know that F is equal to M into A, or F is directly proportional to U, and F is equal to K into U, and Ku, where Ku is equal to M into A. Okay. Now acceleration equal to U into K by M. That is, okay, U into K by M, or U into 2 pi by T whole square. Generally, short buildings are stiffer than the taller buildings. It means short buildings vibrate faster than the tall buildings. For one story, single degree of freedom, time period is 1 by 2 pi into root of m by k. The derivation of this formula can be obtained from this force equation, as the force is directly proportional to the relative displacement with a constant of stiffness constant and other parameters, as it is a sinusoidal simple harmonic motion. So by that we can derive this formula. Okay, now actually I want to explain this why our structures are affected by earthquakes. In generally light buildings which are hit by earthquakes, they will not be affected much. But when we add mass at the top, there is a difference in the motion at the base and at the top. That is nothing but the relative displacement, and it causes forces in the building. Like a simple frame, I am considering a simple frame. When you add mass at the top and a certain force exerting on the building, okay, due to this force, your building moves, and this displacement of the building occurs, and this is called the relative displacement due to this force. Okay, so due to this relative displacement, you have forces generated in this building. Well, if you multiply the relative displacement with the stiffness of the building, we will get the shear force used for the design of a building. Well, we used here acceleration in place of the relative displacement, because when we multiply the acceleration with the mass of the building, we will get the shear force. If we divide the shear force by the mass of a building, we will obtain the acceleration of a building. In summary, we get acceleration as u into k divided by m, or equivalently u into square of 2 pi by t whole square. This equation is used to get the response of an earthquake in place of the relative displacement. So now in structural analysis during the earthquakes, when you take acceleration on the y-axis and time on the x-axis, and your response is something like this. You are mainly concerned about the maximum value of the maximum magnitude of the force, because you don't consider, you are not interested about the direction in which the force is acting and at what time it is acting. You are mainly concerned about the magnitude of that force, maximum magnitude. For a single degree of for a single degree of freedom structure, the maximum response of the structure due to the earthquake depends upon the natural time period. For demonstrating this effect, let us consider a building, a normal frame with zero point 0.2 seconds of time period exerting a force or earthquake force of E1 and measuring its acceleration, and by creating a graph like this. Let us keep a mass m with certain height and time period of zero point 0.2 seconds with the earthquake force of E1. And for this structure, let us assume that we get the maximum acceleration of this value. And now, by increasing its height, let us now fix the same mass. By increasing the height, let us make time period as 0.4 seconds and again measuring its acceleration due to the same earthquake E1, like this. Now, by changing this time period to zero point 0.6 seconds to almost 2 seconds, we'll get the response of this structure for a earthquake of E1. Similarly, for any single degree of freedom building for an earthquake E1, now we can get the maximum acceleration by using this graph. This is nothing but the response spectrum for that earthquake. So, if we find the natural time period of a building as some you like 0.9 seconds, then what we will do, we will just draw a graph, directly go to the this maximum acceleration, and from there, from this point we'll get here, and after getting the maximum acceleration, we'll get the maximum shear force required for design of the earthquake is mass of the structure into acceleration. So for any single degree of freedom, we can use this formula and we can get the maximum shear force in the structure. Now, similarly, for an earthquake of E2, sorry, for an earthquake of magnitude E2, we also make the similar study like what we have done for the time period. This is the time period, and this is acceleration. And for example, this is our. Let us assume that this is our first graph which we got for E1, and now this is the second graph which we got for the earthquake E2, and this will be the third graph which we received for earthquake E3. So like that, so like this, we got one response spectrum By using this, we got one envelope response spectrum. So this is the maximum expected acceleration to occur to a single degree of freedom one-story building due to the earthquake. This is the response spectrum. Okay. Spectral acceleration, SE. Well, do we need to always analyze earthquakes E1, E2, E3 for a specific building whenever we want to get a response spectrum, like what we have done previously? So this is a cumbersome process. So how to obtain the response spectrum curves? If we know the location and the soil type, we can use design codes such as ASCE7 to obtain the response spectrum curves. So the obtained response spectrum is called the envelope response spectrum. This is nothing but maximum expected acceleration to occur to a single degree of freedom one-story building due to earthquake. What I mean is we can obtain the response spectrum curves using simple equations as per this code. So now once we have seen that how after getting your location and type of soil, how to find SS, S1, TL from the code maps and FA, FE from the code tables. So by using these values, we get SDS as SD1 as TS and T0. And already we know that TL is 8 seconds. Once after knowing these parameters, now we can draw the response spectrum curves using ASCE 710. Same, yani Saudi building code also same codes. So like this you can use. You have here T0 value, and this is your TS. and this is your SDS into zero point 0.4 plus 0.6 T by T naught, or let me put it other way. This is this value, and your graphs will look like this. This is whereas this is your TL, this is SD1 by T, and this is SD1 into TL by T square. Okay.